Okay, so I will be talking about the GaN HEMT characterization modeling. Just outline lot of things. So let me just start. This is my group, and we work on industry standard ASM HEMT model. That's our model, and we work with a lot of companies, including EDA companies who are implementing the model. Foundries providing the devices, and even MCAD we were working at some point of time. I think Jacharia is here, he was here, yeah. Yeah. So in my lab we work all the way from atomistic level to RF circuit design. So we have all different types of tools, etc. So atomistic simulation, compact modeling, DC to RF characterization, and RF circuit design, including LNA, PA, and switch. We have all the hardware required for GaN characterization. So we have CMOS. For CMOS we have B1500A, we have PIV system from MCAD, we have two VNAs, one for low frequency, other one for high frequency, and this one is especially useful for self-heating characterization compared to the PNAX, which starts from 500 megahertz. That's B1505 for especially for the power devices, and this is the noise figure NFA, noise figure analyzer, which works for us in our case up to 26.5 gigahertz. And this is the load pull characterization system which we have from Mori. Again, it works very well with the MCAD system also. So this is a passive load pull. The power level goes up to 15 watt, and frequency is up to 18 gigahertz. The tuner works, it's 0.6 to 18 gigahertz, and yeah, we do plan to extend it. We have all types of softwares required for different simulations. Now let me come to the introduction to ASM HEMT. So all of you have been hearing about the models. There are a lot of models, and there are more models coming up, including IIT Madras model. So some of the famous models are like Angelo model, which has been used in the industry for GaN, right? And then there have been models which have been adopted from low voltage MOSFETs like BSIM or BSIM SOI or LDMOS, like those things. So in compact modeling, which I teach for a semester, I teach about all these things. So in one slide, just there are three approaches you can use: table based, which is just like you use the measured data, measure it and use it; empirical model, which is, if I can say, the GaN Angelo model; and the physics based models. There can be again different approaches: charge based, which Amitav explained, threshold voltage based, and surface potential based, and ASM HEMT model is the surface potential based model. This is the group at IIT Kanpur. Some of the students have graduated, and Sajid, who is here, is still working on it. So it starts with the analytical solution of Poisson-Schrodinger equation. We get the 2dg charge density and surface potential. Then we use the drift diffusion equation to get the transport part. Then on top of that we add other effects like Dibble, self-heating, etc., and then the higher order effects like trapping and all those things. So this is a picture summarizing that the core model is there, and on top of the core model we add all other effects one by one, so that the model captures the real device physics which is there. And these are some of the core parameters, but these are just some of the core parameters. There are few more parameters which are there, and this is just a representation of the current as a function of surface potential. This is the extraction flow. So we start with the definition of the technology part, so length, width, T bar, etc. Then you start the extraction. So it's similar to the MOSFET, where you start from the sub threshold, you go to strong inversion, then you go to IDVD, linear, saturation, etc. So, similarly it is like this here also, and then you keep on moving, and once you have done it for the nominal temperature, then you go for the temperature parameters and the capacitances. So, this is just showing how the step by step the parameter extraction is done. First in the subthreshold region here, then in the low VDS linear region, strong inversion, in this case it is above V off, and then we go for IDVD, and then we go further IDVD including the velocity saturation and the excess region velocity saturation effect and the self heating effect. So, these are the again written there the parameters which are needed for different parts of the fitting the different regions. Okay. Excess region is very important, and here the excess region sees quite good amount of electric field which causes velocity saturation in the excess region. So, this has been modeled as a nonlinear function of current. And recently we worked on improving this model, and have published a work where we actually found a problem with the current based descriptions, and now we have moved to the voltage based description of the excess region. So, that is modeling of velocity saturation. This especially causes a problem with the transient in the transient simulation. So, now I am showing you the validation. So, this is the that's the good thing with the model. When you have a physics based model, you can actually dedicate and describe the different regions. So, you have the mobility effect, then you have excess region effects here and the self heating effects. So, you can explain and describe each effect on IDVG and IDVD curves. Okay. So, here for example, there you can see effect of high excess region at high VG. This is very similar to what in LDMOS there is a quasi saturation effect, right, and that is the reverse characteristic, which again this device needs to work in both, can have VD or VS opposite also. So, that is the reverse, and all of this is the validation with the measured data. Then the temperature. So, we have the temperature dependence captured through parameters. These are the temperature, some of the temperature parameters. So, this is showing the on resistance versus temperature and the normalized mobility versus temperature, and then you can see this is again like V off is there are these two parameters which is the for temperature, that is the KT1 parameter. Similarly, the mobility it is a UTE parameter, VSAT has AT parameter like that. Okay. So, this is validation for different temperatures. So, this is for 100 degree Celsius, minus 20 degree Celsius, IDVD, IDVG and IDVD, IDVG. And then the scaling is geometrical scaling is already captured in the model. So, the charge scales with the L and W, current W by L, excess regions are again scaling with the geometry. Then the noise models are also there, and the gate current model, which is very simple model in our case, and so this is how it is. Now, let me show you the validation on the power device. So, we have power, this is the power MOSFET or power GaN HEMT. So, this is the room temperature output characteristics. So, IDVD, the GDS and the derivative of GDS. And this is the reverse side. So, you have ID VD negative voltage, reverse output conductance. So, that is GDS and that is the derivative of GDS. So, you can see the demand from the model how accurate it has to be. The second derivative of current has to really capture the major data, right. Then this is IDVG and that is the GM and the derivative of GM. Okay. This is log scale, again IDVG, IDVD log scale, this is IDVG log scale, and that is the log scale of the reverse side, ID versus VD going in the negative voltages. Okay. And again, as I said, even the log scale yet has to be very accurate. So, once you have a good model, you can really do it well in all regions of operations. Okay. And then this is showing for different temperatures. So, minus 20 IDVD, GDS derivative, reverse output characteristic derivative, and again further derivative of that at minus 20 C, ID VG transfer characteristics and derivatives at minus 20. This is at 100 degree Celsius, IDVD and derivative, IDVG and IDVD VG log, 150 degree Celsius, IDVD log derivative and further derivative of that. Then for the next part is the field plate modeling. So, field plate we model it as a separate model of the transistor. So, depending on the connection, if it is a gate field plate connection, you can see that T1, T2 are connected together, and if it is the source field plate connection, that is the gate of that is connected to the source, right. And we very well know that everybody knows that the field plates are used to minimize the peak electric field and distribute it over the over some area, right, or some length. Okay. So, this is a device which we had data and the different types of connections here shown for the field plates. So, the field plates especially affect the capacitances, they really do not affect the normal current behavior, right. So, here you see the input, output, reverse RSSS characteristics, and this is that is the plot which is showing what if you switch off one transistor, what if you switch off another transistor, what if you switch both transistors, both field plate transistors, how the behavior is changing. Okay. And this is the validation on the measured data for CISS versus gate voltage, and you see this start there. The V off of this device will be around minus 3 or minus 4, something like that, but actually you can see the capacitance started much earlier around minus 45, that is because of the field plate, right. And then the other capacitances, measured data and the model validation, right. And then we have also done mixed mode ticket simulation and validated the how the drain voltage changes, and you can see that model also is able to capture the using the inductance, or of course all the circuit simulation parts of that thing, and more of this how the drain current is changing with the mixed mode versus the compact model, right. Then we have worked on RF devices. So, again RF devices, this is the data from RF device. Once the DC part is done, we need to have the manifold information, right. So, you need gate, drain and source manifold. This part is captured what is in the box by the core or the ASM HEMT model, and then you need to have these inductors connected there. So, this is how the pad parasitics are being modeled using this symmetric network, and the data is there for the manifold. So, that way we can easily calculate these. Bus inductances are extracted using this information of the Y11, Y12, Y21 etc., and then we extract that thing. So, this is the then if you plot just Y parameters, you can see that you can hide lot of things. So, you really need to normalize that by frequency and then plot, because Y parameters will be changing by orders of magnitude. So, if you really want to see how accurate model is, you should plot the capacitances or imaginary or the GDS, like those parameters extracted from the Y parameter. So, this is the CGS. When you say CGS, it is an imaginary part of Y12, right. Similarly, GM, this will be real part of Y21, right, like that, versus frequency, right. So, this is where, this is how you can see that you should be able to capture the real measured data, right. And CGD is the imaginary Y12, right, and GDS is the real Y22, right, Y22. and this is the bus inductance fitting, which is again you can see all the data and also the S11, S12, S21, S12, right. And this is the large signal fitting. So, you can see the P out versus P in for different biases. So, VD 5 volt, 10 volt and 20 volt, and the current is 10 milliampere per mm and 100 milliampere per mm, both two cases, right. Okay. Including the time domain information you can actually get from these load line. Okay. And this is the how the real and imaginary loads measured versus the model part. And then the load pull simulation, you can see the again validation P out and PAE for VD 20 volt and two different drain current values. Then the self heating is modeled using the standard thermal network using RTH and CTH, and then this can be extracted using this one is we have pulsed one where we have no self heating, other one is with the self heating, and then we extract the parameters for the thermal resistance. A trap modeling part, we have 3 trap models in the ASM HEMT. So, one is this one where it depends on the drain voltage only, and there is option for bias dependent, bias independent. It scales with signal power levels, so it is suitable for RF, and it affects these parameters, which is V of RS RD, the resistances, and the eta 0 Dibble parameter. Then the second option is where it has both gate and drain voltage dependence. It is especially suitable for pulsed IV simulation, right, and it modulates the drain side access region resistance and the parameters in the subthreshold region, which is the V of Dibble and the CDS CD. And the third one is mainly for the power device. It depends on both gate and drain voltage, and it modulates the access region drain side resistance. So, this is the extraction showing here using the pulsed IV measurements. So, this is you can see PIV measurements for different quiescent conditions and IDVG. So, you can see the impact of R on and IDVD, R on and the saturation effect. So, you can see the both of these depending on the quiescent bias conditions, and the model is able to capture this thing. Okay. So, it is a quite cumbersome and tedious process actually if you talk about the trapping, first of all the measurements and then the extracting the data and then fitting it in the ICCAF. It is a quite time consuming process. Now, let me show you other recent works which we have been doing. One is this the dynamic fin width model, which similar to what Amtava was talking about. This was where we see that you have alkane there on top, on the sides you do not have, right. So, this works like a FinFET or double gate transistor, and that top transistor it works like a like the GaN HEMT, right. So, what we did engineering approach. We took 2 industry standard models, one is the ASM HEMT, other one is the BSIM CMG model. Note that this depletion effect has to be captured because the effective width of the 2DEG channel, there is a depletion due to the presence of these side walls, right, of the fins. So, they will affect the effective width of this thing, depletion region, right. So, ASM HEMT is modeling the 2DEG, while the BSIM CMG is modeling this bias dependent width modulation due to side walls, right. So, this we have put there ourselves and then combine these 2 models, and then this is how the flow is that you have BSIM CMG calculate the delta W change in the delta W, and then you calculate the W effective, and then the ASM HEMT will calculate the current part, right. So, this is how it is. You have ASM HEMT and BSIM CMG connected in parallel, but on making sure the width modulation or depletion width modulation is taken care of, and then you need gate resistance and inductances for properly modeling the RF part. So, this is the IDS versus VGS showing the impact of the depletion width or the impact of depletion of that thing, and this is the RF validation part. Okay. Then recently we have been working on also the geometrical scalable self-heating model. So, this is mainly for the self-heating. We are seeing the width dependence, and it is captured using a simple model of inverse dependence on the width part and some width. So, you can see that if I have for 4 different widths this thing, right, we cannot capture that correctly using a, unless we have a scalable model, right. So, that is the and this is, you can see for again 4 different widths here, symbol is the line is without RTH model, that one, right. So, so what we did, we captured that RTH versus the total width, you can see that one, right, and then you can see the IDS versus VDS for the 4 different transistors, the self-heating effect is captured, and then further validated on the full set of IDVG, IDVD, you can see the IDVG, GM, IDVD, GDS, all these things, and also the S parameter validation here. Then we also looked into the width dependence of different parameters. How do we make sure that single model card works for different widths? This is not just self-heating, but the entire again different devices we had. So, this again we saw that there is a dependence of width on some of the parameters is needed to capture the width dependence. So, UA, the mobility degradation, Dibble, etc. Okay. And then the model is then validated for the, and this is especially for the large gate peripheries we are talking about, right. Okay. And the IDVD and the S parameters, right. So, different S parameters including the large signal. So, you can see the P out and PAE here shown, right, and the gain they are shown for different conditions. Then we have also worked on what we see that there is a bias dependent effective velocity which needs to be modeled, especially in the saturation transconductance. So, GM sat in if you try to model, it was not coming out to be perfect, if I can say very accurate, and irrespective of how much tuning you do. And then we worked on this thing, and derivation is there in the paper where you really need to have a velocity saturation parameter or VSAT is dependent on the this VG. Okay. So, this is shown here how the V effective is changing and how the NS, the charge density, is changing with that thing, and there it is shown that if we just use one V effective, it cannot capture the major data, those symbols which are shown. So, if you use some value, you can only capture this part or that part, but not the entire bias range, right. And similarly here this is the GM. So, this is again shown, you can, one is overestimating in some region, other one is underestimating in some region. So, with this effective with this new velocity saturation derivation, now we are able to capture the GM properly and also the all the validation for the RF small signal parameters, and also the gain, FT, and then we have worked on the cryogenic modeling part. So, we have now extended the ASM HEMT for valid for cryogenic parameter cryogenic. So, I am just showing you the validation here for 4.2 Kelvin and 300 Kelvin here, and there were some changes in the model which were needed to capture this thing. Okay, and these are some of the equations which we needed to capture this thing. Okay. And also how the kink effect is changing with the temperature. Okay. And now we are just working on the RF switch modeling. This is unpublished work. So, we have worked on this thing, we have done extensive measurements on RF switch. This is showing you some results and some modeling strategy, and how the output power versus the source power, how the insertion loss versus frequency. I am I have not deliberately shown more data for this thing because we have tons of RF switch data and we are working on this. This is still work in progress, and then there are more publications here which I am not going. So, I am open for questions. Thank you.
Thank you very much for your talk. So it's open question. I have one. Concerning the extraction of parameters, at the beginning you show many DC measurements. So it means that you extract many of the parameters with DC measurements.
Yes.
When you move on pulse IV measurement, so you had some trapping effects.
Yes.
Do you need to modify the parameters you initially find?
Yes. So, answer is yes. It's a iterative process, and also it depends. You can either have it done in parallel together. So, like you have pulse IV data along with the DC data and you start from there, that also you can do, but you need to iterate little bit. Yes.
Okay.
Yeah.
Okay. My other question, my second question is concerning the trapping model. You seem to have only one time constant, but we have emission and capture.
Yeah. So, it's a one time constant. That's how it works for the time being. We have tried other models, but it's all about how much complexity to increase in the model, right? And making sure, guaranteeing that everything converges. Right. So, that's a question of compromise and also work in progress. Yeah.
Thank you for presentation. That all your simulation results and comparison with measured data, we have DC measurements is up to 10 volt now. And what is the gate length of your transistor? I think it's 3 micrometers. So
gate length. Gate length means technology. You are talking about minimum.
Yeah. No, not minimum in your slides. I think it's you compare always measured data with simulation data with gate length of 3 micrometer.
I have multiple data here from multiple companies in these slides.
No,
so,
you have shown, I think, for gate length.
No, what I am saying, whatever data I am showing, it's like every slide or every 3 slides there is a different data. So, which data?
I don't know, because go to the up to 10 volt. I don't know.
Okay, that's
just only one, for example.
Take this one.
No, this one probably. What is the gate length?
I don't even remember, and I may not even disclose if I know.
No, it's possible. I don't know if it's possible. Your model is working.
But it's not 3. I mean, it's either some like 0.5 micron technology or something like that, right?
Okay. So I continue the question of Rafael Somme here. So you said for DC you have some parameters, and pulse IV you need to modify some parameters.
Yeah.
So for S parameter you have to modify it.
S parameters. So we convert S to Y to then extract the parameters for the capacitances and the real parts, right? GM, GDS, and then we just need to model the extrinsic part. The core model is set. So once you have physics captured, in fact DC itself is setting the tone for everything. So once the DC is done, and assuming the capacitances, little bit tuning if you need at all anywhere, then the extra inductances and all that is for the frequency domain you have to change, right, or the extract, then you are done for RF, including the load pull. For example, for load pull we don't do anything. It's automatically coming from model.
Okay. I don't know, with the load pull you have tuner passive, no?
That's our
not active load pull. Okay. So if you have one device, transistor device, you cannot obtain the optimal impedance for the PAE, I think, because
Are you talking about going towards the corner of the
Sure.
yeah, Smith chart? Yeah, of course there is a limit. Yeah.
Okay, thank you.
Yeah.
Just one for do you try to model short gate length transistor? I mean 100 nanometers, for example, or what?
I think
150 nanometer?
the minimum we had was 150. Sajid, do you remember? I think 150 nanometer, if I remember correctly, something like that. Okay, yeah. So up to 100 we have.
And the model is able to take into account the short gate length?
Yes. See, gate length is not a problem. Yeah. Yeah.
Long live India and France friendship.